Welcome to One Chemistry. We are seeing organic chemistry concept. We are going with details and solved example. This video we are going to see Wagner Meerwein rearrangement very detailedly. Basics with 58 solved examples. Those examples from various books and exam. To get the complete understanding, stay tuned. What is inside this video? Basically, we will see what is rearrangement, then Wagner Meerwein rearrangement, then basics, stability of cation and shifts, hydride shift, methyl shift, methylene shift, and migratory aptitude of some migrating groups and extra stable cation. Finally, we will go with 58 solved example that will make you expert in the Wagner Meerwein rearrangement. First, let us see what is Wagner Meerwein rearrangement. Before getting into that, there are many types of reaction: addition, substitution, elimination, rearrangement, degradation, and polymerization. This is the very simple explanation. Rearrangement means it's just juggling of the molecule, meaning the atoms are rearranged to get the new stability. Basically, the atom switch is called rearrangement. Then Wagner Meerwein rearrangement. Basically, the rearrangement due to the formation of cation. Which group will rearrange? Methyl, methylene, or hydrogen. Here I given simple example. The starting metal is alkyl bromide. Cation formation is there. The formed cation is primary. The methyl group shift, you have tertiary cation. So primary to tertiary mean more stable cation, because cation stability is primary, secondary, and tertiary is more stable. Then the reaction completion. So the rearrangement of methyl group happened. So cation with rearrangement is called Wagner Meerwein rearrangement. Basically, catalysts are acid, maybe Lewis acid or Bronsted acid, and solvents are polar. Because intermediate is polar, the solvent should be polar. Then the basics, cation stability. Cation stability, basically the tertiary is more stable than secondary, then primary. The reason can be, you can say, hyperconjugation, because CH3 is electron donating due to hyperconjugation. So more the methyl group, more the stability. Tertiary has 3 methyl groups, so it is stable. So the order you should memorize, then only you can master the Wagner Meerwein rearrangement. Then which group will migrate, or you can say which group will rearrange. Here I shown hydride shift to create more stable cation. Here you have primary cation in the system, hydrogen migrates, create the tertiary cation. This is the Wagner Meerwein rearrangement due to hydride shift. Then the basics 3, methyl shift. Methyl also can shift, create the better cation. Here starting metal is primary cation. Once the methyl shift happen, you have tertiary cation. This is typical Wagner Meerwein rearrangement, going from primary cation to tertiary cation. Then the methylene shift. Here the ring expanded, methylene group migrate, which is CH2 migrates. You have ring expansion, moving from primary cation to secondary cation. Here aim is to create secondary cation, or you can say more stable cation. Even though tertiary is more stable, here prime objective is create better cation, so we stop with secondary cation. Then if you have more migratory group, which will migrate is a real question. So electron density matters here, meaning the electron rich group migrates because the intermediate is cation. So high density group migrates. H- is denser because of small size. Then comes phenyl. It has ring as well as charge. Then you have methyl group. So migratory aptitude decided by electron density. Here it's a similar case in aromatic system. Electron rich ring migrates. Here methyl is electron richer due to electron donating group methyl. Nitro is poorer due to electron withdrawing group. So electron density can be decided by minus IF8 or plus IF8. Minus IF8 decrease the migrating ability, plus IF8 increase the migrating ability. Then the extra stable cation, which is very important here because it decides the direction of the Wagner Meerwein rearrangement. In any case, you have cyclopropyl with methyl attachment. The cation stability is so stronger because the cation can stabilize by perpendicular p orbital. Since the ring is rigid, p orbitals are perpendicular, you are creating extraordinary resonance, so the system is very stable. So in cyclopropyl case, ring may expand or contract to create this cation. Then another important cation, which is bicyclic cation. In the ring, you have bicyclic ring formation, means always trans methyl group migrates. Why? Because it will create non-classical carbocation. It is like cyclopropyl cation. It is on the ring, so it is stable. But more technically, if you look at it, the trans methyl group, the assistance is great, so it attacks. You have trans resistance. So trans resistance means trans methyl group in the bicyclic system migrates. Next, we are going to solve problem because problems are best way to learn the basics because you are learning to the problem, not to the tools. So better solve all the problems individually to learn Wagner Meerwein rearrangement better. Here I given 58 such example. Stay tuned. Let us see the first example. You have benzene in the system, side chain you have alcohol, you are reacting with HBr, it is acid. You have to find what will be the final product. As you expect, Wagner Meerwein rearrangement should happen, but we will see step by step. You have alcohol in the system, you are using the HBr, it is acid, so it attacks the OH group. Acid makes OH as a good leaving group, so OH2 leaves, you have cation formation. The cation is the secondary cation, so chances of tertiary is possible, but more than that, it has the possibility of benzyl cation. So benzyl is more stable when compared to tertiary, so the chances formed by migration of hydride. So hydride migration happen, you have the cation, which is the benzyl cation. Then bromine attacks, you have final product. So starting metal products are rearranged due to the extra stability of the cation. In the next example, you have spiro system, 5-member and 4-member spiro system with alcohol. You are reacting with hydrogen bromide. You should find what will be the final product. Here alcohol is there, you are using the acid, mean definitely cation formation because alcohol makes OH as a good leaving group, so you have the cation. Then you have strain in the system because 4-member ring is very strainful. If you look at the ring strain, ring size will be 3 is much high strain, then comes 4, then 5, then 6. 6 is a less strained system. So here the system tried to attain meaningfully. So 4-member ring will become 5-member there. So ring strain is relieved. You have final rearranged product. If you redraw nicely, you have fused 5-member system with cation on the bridged carbon. So the cation again attacked with bromine. You have final product. Here cation formation not only stabilize itself as well as it release the ring strain. The ring goes from 4-member to 5-member. You have the final product. Then the next example, here you have cyclobutane with alcohol and methyl in the 1,3 position. You are reacting with HBr, you should find what will be the final product. Here you have Wagner Meerwein rearrangement possibility because you are creating the cation by forming the cation in the ring. So OH will be removed as water because H plus OH reacts, you have cation in the ring. Then you have the possibility of most stable cation. As we seen already, cyclopropyl kind of setup. You have the stable cation there. The stable cation stabilized by perpendicular p orbital. The cation rotate like normal resonance structure. So resonance provide extra stability. It creates the ring contraction. Ring contraction is against the stability because you are going from 4 to 3 due to the only factor that cyclopropenyl cation. Then the cation attacked by bromine, you have the final product. Here we seen the unusual case, ring contraction. The ring contraction, the only reason is cyclopropyl cation. The extreme stability create the aromaticity. Here strong stability override the ring strain. So the system is followed Wagner Meerwein rearrangement. Then the example 4, you have cyclobutane. Side chain you have 2 methyl group and alcohol. You are reacting with HCl. You should find what will be the final product. Here alcohol is there as we seen already. As it makes alcohol as a good leaving group. So H plus OH reacts, H2O elimination happen. You have the cation. The cation formation is there. It's already a tertiary cation. But you have the problem of ring strain here. So ring strain open the ring. 4-member ring become 5-member. Ring strain create the rearrangement. So ring open, you have secondary cation due to the methylene shift there. Then chlorine attacks, you have beautiful 5-member ring. You start from 4-member ring, end with 5-member ring, but completely rearranged product. Here why this is possible, because you are creating the strain by moving to the lower stabilized cation. The only reason could be the ring strain reduction should be higher than the cation stability. So whenever you look around the system, if there is a cation formation, you should always release the strain. The ring strain with ring size is 3 is more strainful, then lesser than 4, then 5, then 6. Then the example 5, you have cyclopentane. With side chain you have 2 methyl group and alcohol. Reacting with HCl, you should find what will be the final product. Here you have the chances of cation formation. Since alcohol and acidic condition, alcohol will be a good leaving group in presence of acid because it will be removed as water. So alcohol approach H plus, it form H2O, it form the cation. The cation is secondary cation. You can convert into tertiary cation by the hydride shift. So hydride shift occur, you have the cation formation. Here you may wonder why the ring is not opened. There are the possibility. You have to always look at the final product to achieve the final stabilized cation. Here I given the one possibility. You may expand to 6-member also. So tertiary cation form from the secondary cation merely by hydride shift. Since the reaction happened in the side chain, main ring is not disturbed. Then the example 6, you have cyclohexane with alcohol, methyl. Second position you have cyclopropane. In second position you have cyclopropane, which is fused spiro system. You are reacting with HCl. You should find what will be the final product. Here the same condition. Here acid you are using in alcohol condition. So acid alcohol reacts. You have H2O, which is good leaving group. You have cation formation. The cation near very strainful group, which is cyclopropane. Cyclopropane tried to expand, it formed tertiary cation at the same time. So the strain is very harder here. So strain relieved as well as tertiary cation. Two things promote here, ring strain as well as cation stability. Then if you redraw nicely, you have 3-member to 4-member with cation. So chlorine attacks, you have chloride formation. The concept you have to learn here is ring strain always relieved during the cation formation, which is very common in the Wagner Meerwein rearrangement. Then the example 7, you have epoxide with 2 methyl group. You are using methanol in acidic condition. You should find what will be the final product. Here you are using the epoxide. It's a strainful system. The ring will open in presence of H plus. H plus attacked by O. You have OH cation, which is unstable. So ring has to open and quench it. There are the two possibilities, A and B ring opening. Both are given, but A break give tertiary cation, P break give primary cation. So tertiary cation is stable as we seen already. Finally, you have rearranged product, then methanol attacks, you have the final product. Here cation stability dictate the ring opening. You may call it as reserve selectivity. Ring can open either side, open specifically on A side because of stability of the cation. Here why the problem is given, because no cationic rearrangement here, but real rearrangement occur, not the Wagner Meerwein rearrangement. Then the next example, you have cyclohexane, side chain you have alcohol and methyl group, you are reacting with HBr, you should find what will be the final product. Here typical Wagner Meerwein rearrangement condition. First step, as it attacks the OH, you have H2O formation as a cation, which removes you have the cation formation, which is secondary cation. Simply OH will be a leaving group in acidic condition, form a cation. Here secondary cation forms. So secondary can become more stable tertiary by hydride shift. So hydride shift occur, you have cation in the ring which is more stable, it attacked by bromide, you have the final product. So by now you might realize that whenever there is a cation intermediate, always promote the tertiary cation formation by the rearrangement reaction. So Wagner Meerwein rearrangement only occur to stabilize the cation. Then the example 9, you have benzene with side chain, you have linear form of alkene and substituted ethyl group. You are using acidic condition which is H plus. You have to find what will be the final product. Acidic condition, you are using alkene in the system. H plus attacks the alkene in two ways, but it will only attack the terminal position to create the more stable cation. Here itself regioselectivity comes. H plus only attacks the alkene to form the secondary cation. So secondary cation forms. As we expect, we need tertiary cation. So tertiary cation found by the hydride shift, it occurs. But interesting thing is there is a chances of side reaction, which is Fiedel-Crafts reaction by the ring formation, because rings are more stable when compared to linear chain. So ring forms. If you read on nicely, you have beautiful, completely rearranged product. The concept you have to learn here is you have to always look for the Wagner Meerwein rearrangement possibility and some important side reaction. Here Fiedel-Crafts reaction. Then the next example, you have cyclohexane with iodide. You are using silver nitrate. You should find what will be the final product. Here if you look at it, iodine is the good leaving group. You are using the silver nitrate which in effect remove the iodine. So iodine elimination occur, you have the cation formation. So same story goes, but here methylene group migrates. Methylene group migrates, you have the cation formation at the terminal. So terminal cation forms. Here 6-member ring convert into 5-member ring to create the terminal cation. Even though it's less stable, the reason is promote the very stable, quenched, less strained pathway. So secondary become primary here by ring contraction. Then it converts into tertiary. Finally you have NO2 attack. So final product, if you look at it, you have cation, but ring contraction promoted here due to the extra stability. To create the more stable cation, ring contraction happen. Finally, you have completely rearranged product. Now the example 11, cyclobutane with methyl group, side chain you have vinyl. You are reacting with hydrogen bromide. You should find what will be the final product. We are analyzing the possibility of Wagner Meerwein rearrangement. First step, as it attacks the alkene, nucleophile electrophile reacts, you have the cation. The stable cation form. So H attacks the terminal alkene pi bond. So you have cation. Cation and you have strained full 4-member ring. 4-member ring tried to expand itself, as well as same time it tried to create tertiary cation. Two types of stability created. One is strain is relieved and secondary cation becomes tertiary. So ring expanded. Then bromine attacks, you have final product. Here many important things happening. The important thing I have to say here is you have to master the fundamental like Markovnikov rule to achieve the best results in Wagner Meerwein rearrangement. Then the next example, you have alcohol and sulfuric acid. You have to find what will be the final product. The reaction is simple. You have water elimination, you have cation formation. Always you think for the Wagner Meerwein rearrangement. This example is given since there is no higher stability of cation, the elimination occurs. So whenever you do the rearrangement, always analyze the possibility whether tertiary can be achieved or not. If it is not achieved, it's a normal Wagner Meerwein rearrangement. So be careful with that. Then the example 13, you have cyclohexanol with hydrogen bromide. You should find what will be the final product. Here alcohol and acid, same condition. Acid makes the alcohol as the good living group. You have cation formation. When the cation is formed, the chances of Wagner Meerwein rearrangement, the cation should rearrange to achieve the best stability. Because tertiary cation formation is possible, for that ring contraction should occur. So secondary cation become primary by ring contraction, then tertiary formed by hydride shift. Here difficult things to imagine, but you try to achieve the tertiary cation. Then bromine attacks, you have the final product. Here you may wonder why the ring is contracted. Ring contraction occurred here to stabilize the cation. Secondary become primary, last become tertiary, most stable cation. Here priority is charge quenching rather than the ring strain. Then the next example, you have bicyclic system with rigid carbon. Other end you have dimethyl and alcohol. You are reacting with hydrogen chloride. You should find what will be the final product. Here alcohol is there, you are using the acid. Acid makes alcohol as a good living group as H2O. So H2O elimination occurred, you have cation formation. Then the cation is secondary cation. Chances to become tertiary is possible. So methyl group shifts, you are creating tertiary. So going from less stable cation to more stable cation, methyl group migrates, you have cation at the nearby carbon. Then chlorine attacks, you have ring closure there. So if you read on nicely, you are starting from alcohol, end with rearranged chloride there. Why we are redrawing? To get the perspective of starting material to product. The concept you have to learn here is, even though in the bicyclic system, methyl group can migrate to create the more stable cation. Then the example 15, you have cyclobutane, side chain you have bromine with 2 methyl group, you are reacting with ethyl alcohol. You should find what will be the final product. Here you have bromine which is in the tertiary position, so chances of tertiary cation formation is higher. Typical SN1 mechanism, cation formation occur by bromine elimination. The cation is already tertiary, but we have ring strain here. So priority of ring strain release is higher than the stability of cation. Tertiary cation becomes secondary through ring expansion. Here ring strain is relieved but cation stability is reduced. So if you read it nicely, you have cyclopentane, you have cation which is quenched by ethyl alcohol, you have ether there. Here the concept you outline here is, whenever the cation, ring strain always will be relieved, even though with the expenses of cation stability. Then the example 16, you have cyclopentane, side chain you have alkene, you are reacting with hydrogen bromide. You should find what will be the final product. Here you have alkene reacting with acid. It can attack either way in the alkene because it's an electrophilic addition like Markovnikov rule, always stable cation form. So attack happen at terminal, you have cation at the second carbon. So cation forms. As we discussed already, priority of ring strain relieving is higher. So ring strain relieved, you are going from secondary cation to again secondary cation. So two secondary cation form here. Then if you read it nicely, it's a cyclohexyl system with cation. Again the hydride shift can create the tertiary cation. That is our motive, to create the more stable cation. So ring expansion leads to secondary. Then we convert into tertiary by hydride shift. Bromine attacks, you have the final product with bromide. So starting from cyclopentyl ring, end up with cyclohexyl ring. The concept you have to learn here is whenever strain in the system, it will be always relieved during the cation formation. Next, example 17. You have pinene architecture with alcohol. You are reacting with HCl. You should find what will be the final product. As we seen already, alcohol and acid reacts mean acid makes alcohol as a good living group as a water. So first step H plus OH reaction, H2O elimination. Then you have cation. Here the cation form here is secondary cation. Then it is converted into tertiary cation. Then you have strain in the system which is 4-member ring, which will become 5-member ring by reduce the strain. So 6 to 1 methylene shift happen, ring open, 4-member to 5-member. Then chlorine attacks, you have the final product. If you redraw like starting material, you have completely rearranged product. What you should learn? Even in the complex system, Wagner Meerwein rearrangement is possible, but always careful with the structure and rearrange structure. Always redraw the molecule to the same simple way. That is the only way to achieve the best results. In the example 18, you have fused system which is cyclopentane with alcohol. Both sides you have benzene as a fused system. You are reacting with HCl. 3 possibilities are given, but one is phenanthrene given as the major product. You should find why others are not possible, why phenanthrene is the major product. As we discussed already, the possibility of Wagner Meerwein rearrangement with alcohol. Alcohol acid reacts. Acid makes alcohol as the good living group. So cation formation. The cation is formed. The cation is primary cation and it is also not involved in the resonance. If ring open mean it will become secondary cation as well as benzyl cation. It is very stable. It involved in the resonance. So it forms. So if you redraw nicely, you have 6-member ring with cation and possibility of aromaticity. So higher aromaticity is established because final is phenanthrene by hydrogen elimination. So alkene form create the aromaticity here. Here many factors are there. You are starting from lower aromatic system to higher aromatic system and you are releasing the ring strain. You are making 5-member ring to 6-member ring. Then the example 19, you have bicyclic system with bridged carbon, 2 bridge methyl groups and alcohol and methyl at the bridged carbon. You are reacting with HCl. You should find what will be the final product. Here you have alcohol in the system, UR is in the acid. Acid and alcohol react, you have cation formation. Same story again and again, but you should learn properly. Here cation in the bicyclic system, as we discussed already, non-classical carbocation transposition migrate because it is perfect anti-periplanar position. Methylene shift happen, you have non-classical stable cation. The cation at the bridged carbon, but bridge is vanished. So if you redraw nicely with the bridge, because bridge is with lower number of ring size, so bridge with single carbon, you are creating third position same cation by redrawing. Then chlorine attacks, you have the final product. Here one important fact you should learn here is anti-periplanar CH2 shift. Why? Because position is perfect for water elimination. Second, it will create non-classical very stable cation. Then the example 20, here you have spirane system. One side with cyclopropane, another side is with epoxide and side chain alkyl groups. You are reacting with acid, you should find what will be the final product. Here first step is attack of H plus to epoxide. So obviously cation formation it has to be quenched. So two way it will be quenched by opening the ring. You can open A pathway or B pathway. Both are given. A pathway leads to the tertiary cation definitely. But P pathway is very stable because it creates a stable cyclopropyl cation with methylene position. Already discussed, it's a superior stable cation forms. So P break is possible cation form which is very stable. Then the ring open, you have again cation near the alcohol. So cation near the alcohol leads to the carbonyl because it has to quench. Finally, you have quenched product. Here regio selectivity is there because two rings are opening A and B, but the ring opening regio selectivity is decided by the stability of cation. Even though both are tertiary cation, B path leads to the superior cation, which in turn creates the regio selectivity. It's a kind of Wagner Meerwein rearrangement dictated by cation stability and complete carbon skeletal change. Then the next example, you have cyclohexanone, alpha position you have cyclobutane. You are using acidic condition, you should find what will be the final product. Here you have carbonyl and acidic condition. Obviously protonation happen at the oxygen. Then you have cation formation at carbonyl. The ring can expand because cation form nearby carbon. So ring expand, you have new cation formation which is in the alpha position. Then if you redraw nicely, then the cation has to quench. So cyclohexane contracts, you have 5-member ring with cation near the alcohol. If you redraw nicely, you have spiral system with 2 5-member ring, cation near the alcohol. Alcohol quenched as the carbonyl, you have the final product. Here two shift in the ring is there. One ring is expanded, one ring is contracted. The reason is to create the stability and the charge quenching. So two shifts, two different possibilities. Then the example 22. You have cyclopropane, side chain you have methylene chloride, OH minus you are using. You should find what will be the final product. Here you have chlorine which is a very good leaving group which leads to the stable cation. Whenever there is a stable cation, you might know already it's a SN1 reaction, SN1 intermediate. The cation formation is there. Here you may wonder whether the ring expand or not. Definitely ring won't expand because the cation is superiorly stable. We discussed in the basic. It's a kind of cyclopropyl methylene cation. It stabilizes extra by the resonance. The superior stability keep itself. So OH minus attacks. You have simple conversion reaction Cl to OH. It's a simple SN1 reaction, SN1 product. Here the fact you should learn here is if the cation is stable, rearrangement is not required. So no Wagner Meerwein rearrangement is here. But cation stability is important. Ring expansion not occurred is important. Then the next example, you have bicyclic system with alkene in the side chain, 2 methyl groups. You are reacting with HCl. You should find what will be the final product. You have alkene in the system, H plus attacks. You have stable secondary cation formation, not the primary. The cation formed the trans resistance by anti-periplanar methylene group. So non-classical carbocation forms, it stabilizes. You have cation at the bridged carbon, but carbon skeleton change. The skeleton should be rearranged. The cation will be attacked by chlorine. You have chlorinated product. If you redraw nicely, you have chlorine substitution with unexpected product skeleton change. Why we redraw here? Because the cycle on the bridge should be containing less number of carbon atom. Then the next example, you have benzene. You are reacting with propyl chloride, which is N-propyl chloride, and aluminum chloride. You should find what will be the final product. Here you have propyl chloride. If you redraw with carbons, you have chlorine in the system. Aluminum chloride you are using, which will pull the chlorine out, form AlC4-. So cation formed in the system. So cation is formed. The cation is secondary cation. The cation can attack, but it can form tertiary cation, but it can form secondary cation, attacks the benzene ring. So rearranged reactant can attack the benzene ring, Fiddle Crab's alkylation. So long chain, always you get the rearranged product because hydrate shift can occur. You have finally rearranged stable cation. Here primary cation convert into secondary, then attacks the benzene ring as a electrophile. Here we are seeing the application of Wagner Meerwein rearrangement because the reactant, the Wagner Meerwein rearrangement happened not with the starting material. Then the next example, you have the alcohol which is in the linear branched chain at the terminal. You are reacting with concentrated sulfuric acid. You should find what will be the final product. Here as we discussed already, alcohol acidic condition as it makes alcohol as the good living group. So you have cation formation. The cation is not stable. So what really happened? You need to have hydrate shift. So secondary cation should become tertiary cation. Here secondary cation stay as a secondary cation. Here secondary cation can become tertiary cation by two-step rearrangement. Here I written directly. So cation with hydrogen, it has to be quenched. So hydrogen elimination, you have alkene at the final. This reaction can be written in many ways. One of the method is just form secondary cation and end up with final same alkene there. The concept you have to learn here is always stable cation form. There is no quenching pathway. You end up with alkene. Then the next example, you have linear chain with terminal methyl groups and alcohol. You are reacting with the alumina. You should find what will be the final product. Here you are using aluminum oxide. Aluminum oxide is the Lewis acid, but it won't promote the cation formation. Here cation shown to achieve the clarity. Here hydrogen eliminates at the single step with alumina elimination. You have alkene as the final product. Why this reaction is important? Because the cation don't form in no Wagner Meerwein rearrangement. In normal case, cation form in hydrate shift occur. You have cation formation. So many things are possible. Here no rearrangement, no cation formation, no extra skeletal change. So alumina don't promote the cation formation. It form concerted elimination of hydrogen and OH. You have final alkene there. Then the next example, you have cyclobutane. Side chain you have carbonyl group with methyl magnesium chloride and hydrogen chloride. You should find what will be the final product. Here starting metal is carbonyl. You are using methyl magnesium chloride. So nucleophilic addition happened. CH3 adds, you have OH and you have HCl in the system. OH and HCl, chances of Wagner Meerwein. H2O eliminate, you have cation formation. Cation is there, you have strain in the system. So 4-member ring will become 5-member. The strain is removed there. Then the cation can become tertiary cation by hydrate shift, hydrogen shift. You have cation which is tertiary cation. Then chlorine attacks, you have final product. If you read nicely, you have 5-member completely rearranged product. Starting metal is aldehyde, product is simple chlorine. What you should learn here is the strain will be always relaxed from the system if there is a cation formation. Here 4-member ring become 5-member. Then the example 28, you have fused system cyclohexane with cyclopentane. Amine is there. You are reacting with sodium nitrate and HCl. Water you are using. You should find what will be the final product. Here amine is there. You are using NaNO2 HCl diacetization situation. So N has to become N2 here. So functional group conversion. N has to become azo there. It is the cation. It's a salt, diazonium salt. It can be removed as N2. In that system, N2 can be removed from the cation because N2 is the leaving group. It's a gas. It leaves. It has cation. So cation near the strainful 5-member system. So ring will open. So ring open. 5-member ring becomes 6-member. The cation becomes secondary cation. So primary to secondary stability is achieved as well as ring strain is released. Then water attacks, you have the final product. Two important things happen here. One is ring strain release and stability of cation formation. One more important thing is diacetyrization in aliphatic system leads to the cation formation. This is the one more pathway for cation generation. Then the next example, you have fused system with conjugated ketone and you have fused cyclohexane with methyl group in acidic condition. You should find what will be the final product. Acid you are using carbonyl in the system, so protonation happen, you have the cation. The conjugation in the system promote the traveling of charges. So charge travels, the cation form near the methyl group. So the cation try to form itself by methyl generation. Secondary cation become tertiary by the methyl shift. So stability occurs. The cation form near the bridged carbon. Then the cation is quenched by hydrogen shift. More importantly, aromaticity is established here. You are starting from non-aromatic system, end with aromatic. Here, through the cation mobility, through the Wagner Meerwein rearrangement, you are creating the aromatic, more stable system. The concept you have to learn here is always you have to master the basics, not only the cation formation as well as other stabilizing factor, including aromaticity. Then the next example, you have bridged system with two methyl group, alkene and alcohol. You are using metaperchlorobenzoic acid. You should find what will be the final product. Here alkene in the system, alcohol and methyl group. You are using metachlorobenzoic acid. So what happened? Epoxide forms. Epoxide formed as XO because of steric methyl group. Acid attacks, you have ring opening of epoxide. So primary cation forms. Then another possible ring opening occur, which is tertiary cation. So obviously major will be the tertiary cation, which is on the ring. So if you read nicely, it's a kind of pinene system. Cation is there. The cation has to be quenched. How it will be quenched? Methylene group migrates by cation near the alcohol. Cation quenched as carbonyl as well as shift of the methylene group. If you read nicely, you have completely rearranged product. It may look like alkene become carbonyl, but it is a completely rearranged product. The concept you have to learn here is always look for the stability in the system, both in terms of cation stability as well as ring strain stability. More relaxed system always forms. Then the next example, you have beautiful cyclohexane with all position you have cyclopropyl group. At 6th carbon you have methyl and alcohol. You are reacting with hydrogen chloride. You should find what will be the final product. This is the beauty of chemistry. Continuous Wagner Meerwein rearrangement happen here because you have many strainful three-member ring. First step will be obvious formation of cation. Cation near the strainful ring create the ring opening. So continuous rearrangement is possible. At first step ring expands, you have cation near another cyclopropyl ring. Then that ring open. So continuously cyclopropyl ring open. So 3-member become 4-member. So continuous reaction leads to the beautiful continuous cyclobutane architecture. 5-cyclopropyl convert into 5-cyclobutyl and you have terminal cation which will be quenched by chlorine. Finally you have completely rearranged final product. This is called cation cascade. Cation continuously travel through the system, completely alter the system, completely alter the carbon skeleton. Then the next example, cyclopentane, side chain you have alkyl group. You are reacting with hydrogen bromide. You should find what will be the final product. Here you have alkene, you are reacting with H+. So Markovnikov addition happens, stable cation forms. Here secondary cation is stable than primary. So secondary forms, then the cation near the strainful ring. The cation open the system, 5-member becomes 6-member, ring strain is relieved. If you read down nicely, you have 6-member system. Still it is a secondary cation. So secondary cation can become tertiary by hydride transfer. Hydride transfer, you have stable tertiary cation. So tertiary cation quenched by bromine, you have final product. The concept you have to learn here is whenever there is a cation formation, always ring strain will be released. Then the next example, you have pinene system with alcohol as a side chain. You have 3 different methyl groups. You are reacting with HPR. You should find what will be the final product. This kind of example we already seen. We will see the different perspective here. Alcohol is there, acid you are using. So H2O elimination is possible. H2O eliminates, you have cation in the system. The cation is secondary cation. Secondary cation can be converted into tertiary by hydride shift. So cation form. The same story here. 4-member strainful ring become 5-member by relieving the strain. So cation switch happen. Even though cation stability is reduced here, but priority of ring strain reduction is higher than the cation stability. So ring is open, 4-member become 5-member, secondary cation forms. Then the secondary cation quenched by chlorine, you have the final product. Then the next example, it's a carbonyl system which is bicyclic system with 3 methyl group, 2 on the bridge, 2 on the connecting carbon. You have the alcohol. You are using HCl. You should find what will be the final product. Here you have alcohol in the system, acidic condition you are using. So alcohol will be removed as H2O. You have cation formation. Cation in the perfect position of methylene group which is anti-periplanar. So methylene group migrates. You have non-classical carbocation. If you redraw nicely, because you have to redraw to have bridge with less number of carbon atom, you have cation there. Then the cation has to be quenched. Chlorine attacks. You have the final product. Here complete carbon skeleton change. Bridge become part become bridge here. So completely rearranged product because of non-classical carbocation stability as well as anti-periplanar methyl group migration. In the next example, you have cyclohexane which is in the spiral position with 3 alternative cyclopentyl group and 3 alternative hydroxyl group. So highly substituted system. You are reacting with HCl. You should find what will be the final product. Here you have alcohol. You are using H plus which leads to the cation formation because acid makes alcohol as a good living group as a water. Cation form near cyclopentyl. It's a strainful ring. So ring try to open itself. The mobility of cation happened. So cation mobilized and you have ring opening. Ring becomes 6-member and cation quenched as alkene. Second H plus attack. Second alcohol form. Ring expands. You have alkene again. Again third alcohol attack by H plus cation formation. Ring opening. Finally you have alkene formation which become aromatic compound. So you start from non-aromatic compound, end with aromatic compound, which is a high driving factor because aromatic systems are most stable system. The beautiful of chemistry here is 5-member ring keep on expanding itself. Same time it creates the aromaticity. So 2 driving factors here, ring strain reduction as well as aromaticity drives the reaction. Then the next example, it is very simple alcohol with HCl. You have to find what will be the final product. Here alcohol is there, H plus is there, same story. Still eliminate as H2O. So cation form there. Cation is the secondary cation. It becomes tertiary by methyl migration. So methyl shift is there. You have secondary cation to tertiary cation. So finally you have cation, but it has to find the quenching pathway. So it will be quenched as alkene by hydrogen elimination. So if there is no quenching pathway, always alkene is the final product of cation formation. The concept you have to learn here is always you should find the cation quenching pathway. Then the next example, you have cyclopentane, alkene is there, 2 methyl group, hydrogen bromide you are using. You should find what will be the final product. Here H plus attacks the alkene. It can attack two-way, but stable cation always form. So H plus attacks in the connecting carbon, tertiary cation forms. Here you have cation strainful system because it's a 5-member ring. It is strainful. So ring open, you have 5-member ring to 6-member ring. Strain is relieved. So the ring open, cation form. Even though it is a secondary cation, but our priority is ring strain reduction. If you redraw nicely, you have 6-member ring. Then bromine attacks, you have the final product. The concept you have to learn here is priority of ring strain reduction is always higher than the stability of the cation. Then the next example, you have cyclohexene system with exocyclic double bond and rigid methyl group. It's a kind of pinene architecture. You are reacting with hydrogen bromide. You should find what will be the final product. Here you are having H plus adding to the alkene because it's a electrophilic addition to the alkene. It can add in either way, but stable cation form, which is tertiary cation. You have cation, but strainful 4-member system is there, so strain should be relieved. So the ring open itself, it will become 5-member. So 4-member become 5-member. Tertiary cation becomes secondary cation. Here, priority of cation stability is lesser than the ring strain. Ring strain relieved here. Then bromine attacks the cation. You have the final product. The concept you have to learn here is whenever there is a cation formation, always ring strain will be relieved. Then the next example, you have cyclopentane. Side chain you have vinyl and methyl group. You are reacting with hydrogen bromide. You should find what will be the final product. Here you have alkene, electrophilic addition to the alkene, always stable cation forms. So you have secondary cation there. So secondary cation which is near to the strainful 5-member ring. So the ring tried to open itself to relax the ring strain. So ring strain is relieved. 5-member becomes 6-member, perfect tetrahedral angle. So if you redraw nicely, you have perfect 6-member ring. Then you have cation. The cation becomes tertiary cation during the process. So both things happen. Ring strain release, secondary become tertiary cation. So it will be attacked by bromine. So two stability achieved at the same time. So final product is rearranged, completely new product. The concept you have to learn here is the system always try to reduce the strain, at the same time try to establish itself stable cation. Then the next example, you have fused system 4-member and 5-member system with different functional group alkene, carbonyl, alkyl group. Hydrogen and methyl are specified as seen. You are reacting with hydrogen bromide. You should find what will be the final product. Here you have alkene and carbonyl. You are reacting with H plus. H plus can attack the alkene, but cation cannot form in the ring because it need 120-degree angle sp2 hybridization. So it forms as a secondary cation instead of tertiary. So the ring cation don't form, side chain cation forms. Then the ring establishes itself through the strain reduction. The 4-member ring will become 5-member as well as cation shift happen. So cation is there. Finally it conjugates with bromine. You have finally rearranged fused to 5-member ring. Here one interesting thing happened when compared to normal reaction. The cation initially forms a secondary cation because it cannot form at the 4-member ring due to the bond angle. Then the next example, you have 3-dimensional system cubane. With side chain you have 2 phenyl and alcohol. You are reacting with hydrogen bromide. You should find what will be the final product. Everybody knows cubene is the strainful system because the construct is 4-member ring. 4-member ring is very strainful according to Bayes strain theory. So it will also open. That is the basics of it. First step will be usual cation formation by OH elimination. H plus remove the OH's water, you have cation. The cation is super stable because of phenyl, so that will also help. Then ring strain is nearby, it should be relieved. So what really happened? 4-member ring become 5-member. For our understanding, just quickly redraw the molecule to have cation on the front side. So bring the cation front side, bromine attacks, you have final product. The concept you have to learn here is even with the stable system, Wagner Meerwein rearrangement is possible because it creates the extra stability. Here cubene is stable, but still it will undergo rearrangement to become a 5-member less strained system. Then the next example, you have linear system with alcohol, two different methyl groups, one is dimethyl and monomethyl on the 2,3 carbon. Here 3 different methyl group on the each carbon. You are reacting with sulfuric acid and aluminum chloride, both on the same condition, but only Lewis acid varies. So you should find what will be the final product. Here you are using the Lewis acid. Lewis acid everybody knows it really don't form cation. It will just abstract the electron in the system. So what really happened? Concerted mechanism happened. H2O eliminates. You have alkene formation. Here really no cation formed. So no Wagner Meerwein rearrangement. So aluminum chloride pathway don't create the cation. Everything is concerted. You have normal product, not rearranged product. On the contrary, if you use Lewis acid, here sulfuric acid, OH eliminates the water, you have cation formation. The cation is the secondary cation. Continuous hydrate shift lead to the tertiary cation. So secondary become tertiary by continuous hydrate shift. Then finally alkene form. So both are acid, but one follows different mechanism, another follows different mechanism. So aluminum chloride forms normal concentrated less charged product, but sulfuric acid forms completely rearranged Wagner Meerwein product. Then the example 43, you have cyclopentane, side chain you have alcohol and 2 methyl groups, you are reacting with sulfuric acid, you should find what will be the final product. You have alcohol in the system, you are using the acid, same story. Acid makes alcohol as the good leaving group. So OH eliminates as H2O, you have cation. Then you have the possibility which group migrates. Whether methyl group migrates create the cation or ring expands. We already seen charge quenching is much more important than the cation stability. So 5-member ring will open, 6-member ring converts. So finally you have 6-member ring with tertiary cation. If you redraw nicely, you have cation in the system. It has to be quenched. It will be quenched as alkene. Here the competition of migration happen. Methyl or ring open. Both can migrate, but ring open, which will reduce the strain in the system. The concept you have to learn here is reducing the strain is highest priority more than the migrating aptitudes of the functional groups. Then the next example, you have cyclopentane, which is as the keto form. One side methyl, another side cyclopentane with methyl group. We are reacting with sodium bromohydride and acidic hydrolysis. You should find what will be the final product. Here you are using sodium borohydride, which will reduce the carbonyl. So carbonyl reduced to the alcohol, which will create the possibility of Wagner Meerwein rearrangement. Basically, you are using the Wagner Meerwein rearrangement for your advantage. Next step, you are using the acid. Acid makes alcohol as the good leaving group. Make it as the cation. So cation forms. Cation near the ring, which will open the ring. During the ring opening, secondary cation become tertiary cation, which will also create the stability. So if you read nicely, you have tertiary cation. Then it has to be quenched. what way it will quench? It will quench as a major alkene because CSIR products form. So more substituted product will form. Here many things happening in the same reaction, many concepts. But important thing you should learn here is strain reduction is important more than the anything. Then the next example, you have spirane system. One side 4 member, another side 5 member with alcohol. You are using acidic condition. You should find what will be the final product. The reaction is straightforward. You have strain in the system. Let us see how it will go. First step will be obvious. Elimination of OH as the water because you are using acidic condition. Acid makes alcohol as the good living group. Then you have cation on the carbon, which is the secondary cation. Then the ring expands because 4-member ring is very strainful, high strain system. So 4-member become 5-member by ring expansion. During the ring expansion, you have the cation, which will become tertiary. So ring strain is relieved. 4-member become 5-member. If you read it nicely, fused to 5-member system where you have cation. So cation considers alkene there. More substituted alkene will form because it's a CSIR product. Finally, you have alkene central carbon with 2 fused system. You start with spiro, end up with fused system. The concept you have to learn here is always strain will be reduced during the cation formation in Wagner Meerwein rearrangement. Then the next example, you have cyclohexane, side chain you have alcohol and 2 methyl groups. You are using the acidic condition. We should find what will be the final product. The reaction is obvious reaction, but it involves 6-member ring. Let us see what will happen. First step will be obvious because H plus remove OH as the water. It forms cation. The cation is the secondary cation, but chances of ring opening is there, which leads to the tertiary cation. So two things happen: ring expansion, secondary cation become tertiary, which is more stabler one. If you read it nicely, 6-member ring will become 7-member with tertiary cation. Then alkene forms, but more substituted alkene will form as a CSIR rule. So two important factors, Wagner Meerwein rearrangement and CSIR rule. Whenever there is alkene formation, more substituted alkene will form, which is called CSIR rule. The concept you have to learn here is even 6-member ring will open itself to form the 7-member ring. Then the next example, you have trimethyl substituted propyl alcohol reacting with concentrated sulfuric acid. You should find what will be the final product. Here you have alcohol, you are using the acidic condition. Obvious will be water elimination and cation formation. The cation is the secondary cation. It can become tertiary by methyl because there is all methyl. Any methyl will migrate, you have cation formation. So secondary cation become tertiary, more stable cation. Then the cation has to be quenched. The cation will be quenched with CSIR product because more substituted alkene is stable when compared to less substituted. So the major will be more substituted alkene. The concept you have to learn here is cation quenching pathway also important. The cation quench always with the CSIR rule priority. Then the next example, you have cyclobutane, side chain you have chlorine with 2 methyl group. Methanol you are using, you have to find what will be the final product. Here you have chlorine in the system. Chlorine is a very good leaving group. It leaves itself, so it has cation. So chlorine leaves, cation forms. Cation near very strainful system because cyclobutane has considerable strain because of 90-degree angle. So it expands, you have cation formation. Here you have tertiary cation converted into secondary cation because ring strain reduction is important. So cation forms. If you read it nicely, you have 5-member secondary cation. Then the cation can become tertiary by methyl group migration. It happened, you have tertiary cation. Then the hydrogen elimination. Final product is CSIR product with alkene. The concept you have to learn here is ring strain reduction is highest priority and cation quenching followed the CSIR rule. Then the next example, you have normal system which is bicyclic compound with chlorine and 3-methyl group. You are reacting with tin chloride. We should find what will be the final product. Here the reaction is same but you are using different reagent. So what really happened? It will abstract the chlorine. Chlorine elimination happened. You have the cation formation. So cation leads to the most stable cation which is trans-methylene group migration, non-classical carbocation which leads to the cation in the ring there. You should redraw the molecule with bridged carbon. If you redraw it, cation near the side chain ring, then chlorine attacks, you have the final product. But chlorine can be exo or endo. Exo is major because of bulky chlorine size. The concept you have to learn here is tin chloride can remove the chlorine from the system. It forms cation. Then the next example, you have cyclopentane. Side chain you have 2 alcohol, diol group and 2 methyl group. You are using acidic condition. You should find what will be the final product. You have diol and acidic condition mean technically it's a pinacol-phenaclone rearrangement, but you can consider it as a Wagner Meerwein rearrangement. First step will be cation formation. Cation can form in either way, but the tertiary cation is major. So terminal alcohol remove, you have tertiary cation. So here looking at the stability of cation, decide the major product. Then you have cation nearby strainful 5-member ring. So the ring open, you have 5-member to 6-member and cation mobilized. The cation near the alcohol quench itself, it become carbonyl there. So if you read nicely, you have beautiful 6-member. You start from simple linear compound to beautiful cyclic product. The concept you have to learn here is the strain always will be removed if the formation of cation. This example you may consider it as an advanced Wagner Meerwein rearrangement. Then the next example, normal system with 2 methyl groups and acidic condition. You have to find what will be the final product. Here we have to redraw the molecule with hydrogen. If you redraw it, you have OH and hydrogen. Acidic condition obviously mean you have water removal. OH removes the water, you have cation there. How the cation will be quenched? Here only chance is cation will be quenched by H elimination. So H eliminates, you have alkene formation. That alkene has two possibilities because you can generate it with methyl shift as well as hydrogen shift. Both is possible, but methyl shift leads to the major product because it creates less strain there. It's a kind of little bit advanced example. The competition between hydrogen and methyl. Methyl creates the most stable system, so it is the major product. Then the example 52, you have cyclobutane with alcohol. Reacting with HCl, you should find what will be the final product. This example will be super interesting. Why? Because the cation formation is obvious, but after that what will happen? Here the cation will form from the ring contraction. It's very important because you are forming super stabilized cation. Cyclopropyl with methyl group. The methylene cation is stable. Why? Because it will have resonance kind of architecture which creates extra stability which promotes the ring contraction. Most of the time ring expansion happen. This is the rare situation. Ring contraction happen, form the cation. Then the chlorine attacks, you have the final product. So the concept you have to learn here is it is all about cation stability. If the cation form from the ring contraction, system promote the ring contraction, final product with stressful 3-member ring. Then the next example, cyclohexyl system with many methyl groups and alcohol. You are reacting with sulfuric acid. You should find what will be the final product. Here you have alcohol, same story. Alcohol will be eliminated as water, form the cation. Here cation formed. Already it is a tertiary cation. What really happened is it has to be quenched. So the cation contract the ring like previous example, ring contraction happened. Cation formed at the side chain. Then the cation has to be quenched. How it will be quenched? It will be quenched by the hydrogen elimination because it needs compensating electron pair. So again the methyl group migration to find the quenching pathway, it migrates. You have cation in the ring again. It will quench by alkene formation. It's a kind of very complicated example. That's why I given the last two kind of shift happen to create the ultimate stability. The concept you got learn here is the cation can switch over and over to create the ultimate stability and the stable system of compounds. Then we will see the application of Wagner Meerwein rearrangement because it's used in many synthetic applications. It can be a part of very large molecule synthesis. So it's a smaller part but it plays significant role. Then the next example, here you have trifused system, cyclohexane, butane and cyclopentane, 3 methyl group with ketone. The functional group is ketone. Then you are reacting with phosphorus compound which is Hydride, then tosyl acid. We should find what will be the final product. Here first step, Hydride reacts with carbonyl. It is called Wittig elimination. It forms alkene from the carbonyl, complete functional group transformation. Then you are using acidic condition. So alkene attacked by H+, you form cation. Cation in the ring, but you have strainful system which is 4-member ring. So 4-member ring try to open itself to reduce the strain. Ring open, you have the cation near the ring there. So cation is there. If you redraw nicely, you have beautiful 3-5-member system. So complete carbon skeletal change. Then the cation has to be quenched. Cation quenched as alkene there. The concept you have to learn here is Wagner Meerwein rearrangement can be a part of synthetic molecule. Mostly the surprised molecules will be formed in this kind of reactions. Then the example 55, you have benzene and you have the conversion reaction. You have to convert benzene with 2 substitution. You have to find number of steps and reagents involved in the conversion. Similar example we seen already, but here you have to promote the meta formation. Meta need meta directing electron withdrawing group. Carbonyl is the best one. First step will be Friedel-Crafts acylation. So acylation happened. You have carbonyl attached with the ring, which is the meta director. Then the acylation reaction of Friedel-Crafts, but the cation will rearrange itself because primary cation is less stable than secondary. So secondary forms, it attacks the ring. But reaction happen with meta because CO is the meta director. Then you have to remove the CO group. It can be done by zinc amalgam and HCl. Finally, you have desired product. The reduction is Clemmensen reduction. You are converting carbonyl into methyl. The concept you have to learn here is naming reactions are very important part of organic synthesis. One of it is Wagner Meerwein rearrangement. Then the next example, toluene you have aluminum chloride and you have neopentyl group with chloride. You should find what will be the final product. You have neopentyl chloride, aluminum chloride you are using which promote the cation formation. The cation is primary cation. It can be converted into tertiary by methyl shift. So methyl shift happen. Cation converts into tertiary. It attacks the benzene ring. Since it is very steric, it will only form para. Even though methyl is orthopara director, para is encouraged to reduce the steric effect. Final product forms. Here cation stability versus reactivity defined, steric effect versus reactivity also defined. The concept you have to learn here is mostly bulky molecules involve Wagner Meerwein rearrangement. Then the next example, You have fused system with hydrogen and alcohol are trans to each other and one methyl group. The system is basically a decline system with substitution. You are reacting with phosphoric acid. You should find what will be the final product. Here same acid and alcohol, so you have water elimination. The water elimination leads to the cation formation at the fused carbon, so cation forms. Then you have three possibility for the cation quenching. The hydrogen elimination, cation quenched with hydrogen elimination. How it will eliminate? It will eliminate with the trans product. You have alkene there, the possibility of CSIR elimination as well as anti-periplanar elimination all promote the same product, so no confusion. Here why the example is given mean there is no Wagner Meerwein rearrangement because it has the perfect possibility of stability of the cation as well as quenching pathway is defined. Then the next example, you have fused system 6 member and 5-member lactone and you have conjugated ketone with methyl group. Here methyl groups are stereochemically specified. Ester also below the plane. You are using acidic condition. You should find what will be the final product. Here carbonyl group is there. You are using the acid. So carbonyl prefer with acid mean it form cation there, basically protonation. Then the charge travel, you have cation near the methyl group. Cation near the methyl group is secondary cation. It will migrate, it form tertiary cation. So secondary into tertiary formation by the methyl shift. Then cation quenched with perfect stability, which is aromatic compound. You start from non-aromatic to aromatic, very stable formation. The concept you have to learn here is you have to know the similar factor which can stabilize the cation as well as which stabilize the system. Then we have summary of all the example. What you should know from this video. First you should know migratory aptitude because migrating group promote the rearrangement. More electron rich group migrate. So H- is richer, then comes phenyl, then methyl. Then if you are in the aryl system, electron donating group increase the electron density, so migrate first. Electron withdrawing group decrease the density, which migrate least. Then the most stable cation, cyclopropyl with methyl group. And one interesting example is ring strain. 3-member is more strainful, 6-member is less strainful. So you should master the strain also. Then the aromaticity decides whether the charge quenching follows substitution or elimination reaction. That's all from this video. Thanks for watching. If you have any suggestion or feedback, comment below.